Imagine a world that defies imagination. This is a pulsar star, a cosmic engine of destruction. Pulsar stars are the remnants of stellar explosions, incredibly dense and spinning at incredible speeds. As they spin, pulsars unleash beams of intense radiation, sweeping across the cosmos like cosmic lighthouses. Yet against all odds, there are planets that orbit these celestial infernos. Join us as we journey to these impossible worlds, exploring the science and wonder of pulsar planets. Our story begins with the stars, those distant suns scattered across the cosmos. When massive stars exhaust their fuel, they collapse under their own gravity, triggering a cataclysmic explosion known as a supernova. From the ashes of these stellar explosions, something extraordinary emerges, a neutron star. Neutron stars are among the densest objects in the universe, spinning rapidly and emitting beams of radiation. These spinning neutron stars emitting beams of radiation are what we call pulsars, and it is around these pulsars, these cosmic lighthouses, that we find the most unlikely of neighbours' planets. To understand pulsars, we must first journey into the heart of a dying star. Imagine a star far more massive than our own sun, a celestial giant nearing the end of its life. Eventually the star's core runs low on hydrogen, and the star begins to collapse under its own immense gravity. As the core collapses, it heats up to billions of degrees, forming neutrons. This neutron star is incredibly dense, a state of matter that exists nowhere else in the universe. It's a cosmic implosion of unimaginable force. The collapse of the star's core triggers a shockwave that travels outward, ripping the star apart in a supernova explosion. As the core collapses into a neutron star, it conserves angular momentum, spinning faster. Some neutron stars spin hundreds of times per second, whipping around like cosmic tops. This rapid rotation is one of the key characteristics that define a pulsar. It's what sets these objects apart from ordinary neutron stars, and it's this rapid rotation that gives rise to the pulses of radiation that make pulsars so fascinating. A pulsar doesn't just spin rapidly, it also possesses an incredibly strong magnetic field. This magnetic field funnels charged particles into tight beams that shoot out from the pulsar's magnetic poles. As the pulsar spins, these beams sweep across space like the beam of a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation every time the beam sweeps past us. These pulses are incredibly regular, some as precise as atomic clocks. The precision of these cosmic clocks is still awe-inspiring. The incredible regularity of pulsar signals makes them incredibly useful tools for astronomers. By timing the arrival of these pulses, astronomers can study a wide range of phenomena, from the properties of neutron stars to the structure of our galaxy. One of the most remarkable discoveries made possible by pulsar timing is the existence of planets orbiting other stars. The first exoplanets ever discovered were found orbiting a pulsar, a discovery that shocked the astronomical community. The discovery of pulsar planets showed that our understanding of planetary systems was far from complete. It opened up a whole new realm of possibilities for where planets might exist and what they might be like. The year was 1992. Astronomers Alexander Voltschan and Dale Frail were studying a pulsar known as PSR B1257+12. They noticed slight variations in the timing of the pulsar's pulses, tiny wobbles in the signal. The only explanation for the wobbles was the presence of planets orbiting the pulsar. These planets, too small and faint to be seen directly, were tugging on the pulsar with their gravity, causing it to wobble slightly as they orbited. It was a groundbreaking discovery, the first confirmation that planets existed beyond our solar system. The discovery sent shockwaves through the astronomical community, challenging everything scientists thought they knew about where planets could form and survive. The discovery of the first pulsar planets highlighted the power of a technique known as pulsar timing. This method relies on the incredible regularity of pulsar signals. Imagine a pulsar as a cosmic lighthouse, sending out beams of radiation with each rotation. If a planet orbits that pulsar, its gravity tugs on the pulsar, causing it to wobble slightly. By measuring these tiny variations in the pulsar's timing, astronomers can infer the presence of an orbiting planet. They can even determine the planet's mass and orbital period based on the characteristics of the timing variations. The pulsar timing method is incredibly sensitive. It allows astronomers to detect planets that would be impossible to find using other methods. This is particularly useful for finding planets around pulsars which are much fainter than ordinary stars. The beauty of the pulsar timing method lies in its simplicity and elegance. It relies on the fundamental laws of physics, specifically gravity and the nature of light. The discovery of the first pulsar planets using this method was a testament to the power of human ingenuity and the insatiable curiosity that drives us to explore the cosmos. The discovery of planets orbiting PSR B1257+12 had profound implications for our understanding of planetary systems and the possibility of life beyond Earth. This discovery challenged the very notion of what a planetary system could be. It showed that planets could form and survive in environments far more extreme than we had ever imagined. The existence of pulsar planets raised tantalizing questions. How did these planets form? Did they form in the aftermath of the supernova explosion that created the pulsar? Or were they once part of a planetary system that existed before the supernova? The discovery of pulsar planets was a reminder that the universe is full of surprises, and the more we learn about it, the more we realize how much we don't know. Imagine standing on the surface of a planet orbiting a pulsar. The sky above would be a terrifying spectacle, dominated by the ghostly glow of the neutron star. Pulsars emit intense radiation, streams of high-energy particles that would bombard the planet's surface with lethal force. The surface of a pulsar planet would be a barren, irradiated wasteland, constantly bombarded by lethal energy. Pulsars also possess incredibly strong magnetic fields, generating immense tidal forces. A planet orbiting a pulsar would be trapped in this gravitational well, constantly being pulled and stretched by the pulsar's immense gravity. Given these extreme conditions, it's a wonder that pulsar planets exist at all. Pulsar planets that orbit too close to their host star would be quickly destroyed by the intense radiation and gravitational forces. But pulsar planets that orbit at a greater distance might stand a chance of survival. These planets would still be subjected to extreme conditions, but their distance would offer some protection. The first pulsar planets discovered were thought to be rocky worlds, similar in composition to Earth. These planets would have to be incredibly dense and durable to withstand the constant bombardment of radiation and the gravitational stresses of orbiting a pulsar. Assuming pulsar planets can survive the harsh conditions around a neutron star, how do they form in the first place? The process of planet formation around a pulsar is still a mystery, but scientists have proposed a few intriguing possibilities. One theory suggests that pulsar planets are the remnants of planets that orbited the star before it went supernova. In this scenario, the planets would have been much farther away from the star, orbiting at a safe distance. When the star exploded, these planets would have been blasted by intense radiation and shockwaves, but some of them might have survived. They would have been stripped of their atmospheres and outer layers, leaving behind only their dense, rocky cores. These cores would then spiral inward, eventually settling into close orbits around the newly formed pulsar. Another theory proposes that pulsar planets formed from the debris left behind after the supernova explosion. As the star's outer layers were blasted into space, they would have mixed with the material from the star's core, creating a swirling disk of gas and dust. Over time, debris coalesced, forming new planets around the pulsar. This process, known as accretion, forms planets around young stars. Conditions around a pulsar are far more extreme. Pulsar planets are a testament to nature's resilience. They endure violent cosmic events and emerge as survivors. In the cosmic graveyard surrounding the pulsar PSR B1257+12, we encounter Drauga, a tiny, resilient exoplanet. Named after undead creatures from Norse mythology, Drauga is smaller than our moon. It orbits its pulsar in just 25 days. Drauga endures intense radiation and gravitational forces. Its surface is likely barren, sculpted by harsh conditions. The discovery of Drauga challenges our understanding of planetary formation. Orbiting further out from the pulsar than Drauga, we encounter our next destination, Poltergeist. Named after mischievous spirits, Poltergeist defies nature's laws. It has a mass several times that of Earth, yet it's dwarfed by its host pulsar. Poltergeist orbits at a safer distance, completing an orbit in 66 days. It lies at the edge of the habitable zone, but intense radiation makes life unlikely. Its surface is a desolate wasteland, Poltergeist's orbital dynamics are intriguing. Variations suggest another unseen planet. This hypothetical world, Phobetor, is hinted at by celestial movements. Our final destination in the PSR B1257+12 system is the enigmatic Phobetor. Named after the Greek god of nightmares, Phobetor is inferred from gravitational wobbles. These wobbles suggest a gas giant, similar to Saturn or Jupiter. If it exists, Phobetor would be a dark alien world under intense radiation. Its skies might glow with eerie auroras, a haunting spectacle. Imagine standing on the surface of one of these pulsar planets. The sky above would be a sight unlike anything we can imagine. Dominating the heavens would be the pulsar itself, a celestial beacon pulsing with an eerie, rhythmic glow. The pulsar would cast a strobe-like effect, illuminating the desolate landscape in flashes of intense radiation. The very air would crackle with energy, charged by high-energy particles from the pulsar. The ground beneath your feet would be a barren wasteland, sculpted by relentless radiation. But amidst this desolation there would be a strange beauty. The intense magnetic fields of the pulsar would create spectacular auroral displays. You might even witness the ghostly silhouettes of your celestial companions. Of course, actually standing on the surface of a pulsar planet is pure science fiction. The extreme conditions of these worlds make them utterly inhospitable to life, but that doesn't make them any less fascinating. It is their very alienness that makes pulsar planets such captivating objects of study. They remind us that the universe is a vast and wondrous place full of surprises. The discovery of pulsar planets was a triumph of human ingenuity. These planets were found by deciphering variations in signals from their host pulsars. The technique, known as pulsar timing, relies on the precision of these cosmic clocks. Imagine a pulsar, a rapidly rotating neutron star, emitting beams of radiation. These beams, like a lighthouse, sweep across the cosmos. Pulses arrive with precision, rivaling atomic clocks. This regularity makes pulsars valuable tools for astronomers. Imagine a planet orbiting that pulsar. Its presence can be inferred by its gravitational influence on the pulsar. The planet's gravity causes the pulsar to wobble. This wobble affects the timing of the pulses we receive. Pulses might arrive slightly earlier or later than expected. These variations are incredibly small, often millionths of a second. Modern radio telescopes and dedicated astronomers reveal these unseen worlds. The pulsar timing method is a delicate dance between gravity and light, revealing the interconnectedness of the cosmos. Even a small planet can influence a pulsar, detectable by its effects on the pulsar's light. This light travels for thousands of years to reach our telescopes. The gravitational pull is like a mosquito's influence on a bowling ball. Yet astronomers can detect this faint signal. Despite challenges, the method has uncovered dozens of pulsar planets since 1992. The precision required for pulsar timing is astonishing. Imagine measuring the time it takes for light to travel 1 meter. That's about 3 nanoseconds. Pulsar timing requires even more precision, down to picoseconds. Astronomers use sophisticated instruments and meticulous data analysis. They rely on atomic clocks and complex algorithms to filter out noise. The reward is worth the effort, revealing hidden wonders of the universe. Pulsar timing allows us to detect planets invisible in visible light. Unlike the transit method, pulsar timing detects planets by their gravitational influence. This method works regardless of the planet's size or orientation. Pulsars emit radio waves and X-rays detectable with specialized telescopes. Pulsar timing has revealed diverse planets around pulsars. It shows planet formation is robust, even in extreme environments. The discovery of planets orbiting pulsars posed a profound question. How could planets form in such extreme environments? The intense radiation and gravitational turmoil seemed inhospitable to planet formation, yet pulsar planets existed, defying expectations. One theory suggests these planets are ancient survivors of a cosmic cataclysm. They might have endured the fiery ordeal of their star's death and the subsequent supernova. While the survival scenario explains how pulsar planets might endure, it doesn't address their formation. Could these planets form amidst a supernova's chaos? The accretion scenario suggests so. In the aftermath, a swirling disk forms. This chaotic disk might seed planets. Particles collide and clump together, forming larger bodies. But the environment is hostile. With intense radiation and magnetic fields, can planetary embryos survive? If pulsar planets didn't form in their current orbits, either by surviving their star's demise or accreting from the supernova debris, could they have originated elsewhere and been captured by the pulsar's gravity? This is the premise of the capture scenario, a theory that invokes the cosmic ballet of stellar encounters and gravitational interactions. Imagine a pulsar, a stellar remnant hurtling through the vastness of space, encountering another star system along its path. This encounter, if close enough, could disrupt the orbits of planets in the other system, flinging some of them outward into interstellar space. Some of these ejected planets might wander close enough to the pulsar to be ensnared by its gravity, captured into orbit around this newfound stellar master. These captured planets, having formed in more conventional environments, would suddenly find themselves in the extreme conditions of a pulsar system. The capture scenario offers a potential explanation for the diverse orbits observed among pulsar planets. Unlike planets that form within a star system, which tend to have relatively circular orbits, captured planets can have highly eccentric or inclined orbits, reflecting their chaotic origins. The formation of pulsar planets remains one of the most intriguing mysteries in astronomy. Each of the proposed scenarios, survival, accretion and capture, presents its own set of challenges and uncertainties. It's possible that the true story involves a combination of these processes, or perhaps an entirely different mechanism that we have yet to imagine. The study of pulsar planets is still in its infancy. Each new discovery, each piece of data we gather adds to the puzzle, but also deepens the mystery. The extreme conditions around pulsars make them challenging targets for observation, but astronomers are developing new techniques and instruments to probe these enigmatic systems in greater detail. Future telescopes, both ground-based and space-based, will have the sensitivity and resolution to detect fainter pulsar planets and study their atmospheres, providing clues about their composition and history. These observations will help us refine our models of planet formation and perhaps even shed light on the possibility of life in these extreme environments. The pulsar planets, once thought to be impossible, stand as a testament to the boundless creativity of the cosmos. Their very existence challenges our assumptions and inspires us to explore the universe with open minds and a sense of wonder, knowing that the most profound discoveries often lie beyond the realm of our current understanding. The discovery of planets orbiting pulsars ignited a debate in astrobiology. Could life find a foothold in such hostile environments? It challenges our notions of habitability and the limits of life. The odds seem stacked against life on pulsar planets. Such worlds are bombarded by intense radiation and powerful magnetic fields. Delicate molecules like DNA would be torn apart. Yet life on Earth thrives in extreme environments. From Yellowstone's hot springs to the Marianas Trench, life adapts. Could there be hidden niches on pulsar planets where life endures? The answer remains uncertain but possible. In our search for life beyond Earth, we often look to the extremophiles, those hardy microorganisms that thrive in the most extreme environments our planet has to offer, as a guide to what might be possible. These extremophiles, adapted to conditions that would kill most other life forms, demonstrate that the boundaries of life are far more expansive than we once thought. Take, for example, the tardigrades, microscopic creatures affectionately known as water bears or moss piglets. These remarkable creatures can withstand extremes of temperature, pressure, radiation, and even the vacuum of space. They can survive being frozen solid, boiled alive, and exposed to radiation levels 1,000 times higher than what would kill a human. Another example is the Deinococcus radiodurans bacterium, dubbed Conan the Bacterium, for its incredible resistance to radiation. This bacterium can withstand radiation doses that would shatter the DNA of most other organisms, thanks to its ability to repair its own genetic material with remarkable efficiency. While the conditions on a pulsar planet would be far more extreme than anything these extremophiles experience on Earth, their existence gives us a glimmer of hope that life, in some form, might find a way to endure even in the most hostile corners of the cosmos. If life were to exist on a pulsar planet, it would likely need to find refuge from the relentless bombardment of radiation that defines these extreme environments. One possibility is that life might exist beneath the planet's surface, shielded from the worst of the pulsar's fury. On Earth, scientists have discovered vast ecosystems of microorganisms living deep underground, in the cracks and pores of rocks, far removed from the sunlit surface. These subsurface ecosystems, known as the deep biosphere, derive their energy not from sunlight but from chemical reactions within the rocks themselves. If a pulsar planet were to have a subsurface ocean of liquid water, perhaps heated by geothermal activity within the planet's core, it's conceivable that life could exist in this sheltered environment, shielded from the deadly radiation above. Even if a pulsar planet lacks a subsurface ocean, life might still find a haven in caves or underground aquifers where it could eke out an existence, drawing energy from chemical reactions or perhaps even from the faint glow of the pulsar itself, filtered through layers of rock and water. The possibility of life on pulsar planets is a testament to the boundless creativity of the universe. It forces us to expand our definition of what constitutes a habitable environment. Imagine life forms that harness the energy of the pulsar's radiation. The universe is vast and wondrous, and life may thrive in unimaginable forms. The search for life beyond Earth is a journey of discovery, expanding our understanding of the cosmos. The discovery of pulsar planets shocked astronomers, challenging assumptions about where planets could exist. Exoplanet hunting focused on stars like our Sun. We sought life around stars providing warmth and light. But pulsars were different, dense and emitting intense radiation. Yet pulsar planets existed, proving planetary systems could arise unexpectedly. This discovery broadened exoplanet research, hinting at a diverse universe. The existence of pulsar planets expanded the cosmic landscape for where planets might reside, forcing us to re-evaluate our understanding of planet formation. Traditional models suggest planets form in protoplanetary disks around young stars. But pulsar planets challenge this idea. Intense radiation and magnetic fields should disrupt planet formation. Yet, pulsar planets exist, suggesting robust or alternative formation mechanisms. They push the boundaries of our theoretical models. The discovery of pulsar planets not only broadened our understanding of planetary systems, but also spurred the development of new and innovative techniques for detecting exoplanets. The pulsar timing method, used to uncover those first pulsar planets, proved to be a powerful tool capable of detecting planets that would be impossible to find using other methods. The success of pulsar timing inspired astronomers to refine and adapt this technique for use with other types of celestial objects. One such adaptation is the timing variations method, which looks for minute variations in the arrival times of signals from other types of variable objects, such as white dwarfs and pulsating stars. Just as a planet's gravity can cause a pulsar to wobble slightly, affecting the timing of its pulses, so too can a planet's gravity cause subtle variations in the light curves or pulsations of other types of stars. By carefully analyzing these timing variations, astronomers can infer the presence of planets even if they cannot be directly observed. The discovery of pulsar planets also highlighted the importance of multi-wavelength astronomy. Pulsars emit radiation across a wide range of the electromagnetic spectrum, from radio waves to gamma rays. By observing pulsars in multiple wavelengths, astronomers can gain a more complete understanding of their properties and the environments they inhabit. The search for life beyond Earth has often focused on the habitable zone, also known as the Goldilocks zone. This is where temperatures are just right for liquid water, but pulsar planets challenge this notion. They exist in extreme conditions far from the habitable zone. Life here would be radically different, adapted to extremes. The search for life now extends to the cosmos's most extreme corners. The universe is far stranger and more diverse than we imagined. The journey to understand pulsar planets has taken us to the very edge of what we thought possible. We've explored the remnants of exploded stars, those cosmic lighthouses that sweep the cosmos with beams of intense radiation. It's a story that resonates with our own place in the universe, offering a glimpse into the distant future of our own solar system. Billions of years from now, our Sun too will reach the end of its life. It will swell into a red giant, engulfing the inner planets, including our own Earth. Then, it will shed its outer layers, leaving behind a white dwarf, a cooling ember of its former self. The study of pulsar planets is about understanding our own cosmic destiny. As we conclude our exploration of pulsar planets, we find ourselves with a renewed sense of wonder. The discovery of these worlds has opened up more questions. How do these planets form and survive? Could they harbour life as we know it? We need more data, more exploration. The James Webb Space Telescope promises to revolutionize our understanding. Let us continue to explore, to question, to imagine. For in the words of Carl Sagan somewhere, something incredible is waiting to be known.